Okay, off we go. Looks like we're recording. So, okay, here's where we were last time. We were talking about this question of how do I maximize the directional derivative, which, again, you can ask in sort of different ways. You can say, hey, what is the unit vector pointing in the direction of fastest increase? Or you can say, hey, what is the unit vector that points in the direction of steepest ascent? It depends on how you want to think about it. And again, unfortunately, this is the more common term, even though it really only makes sense in a fairly narrow context. So anyway, you're going to hear me more often than not say direction of fastest increase. I think it makes broader sense. Anyway, heads up. Okay, so how to answer that question? How do we find the unit vector that maximizes the directional derivative? Well, the directional derivative, there's our formula for it. It's a dot product. Here's how we compute dot products. Right? I mean, that's magnitude times magnitude cosine of the angle. And now wait a second. By assumption, this is a unit vector. That means this magnitude is 1. So really, this is what we're trying to maximize. Nice, simple little formula. But here's the further simplification. We're considering all different possible directions from which I might move from the point A. But I'm not actually moving yet, right? I'm still thinking about it. I'm at the point A, and I'm thinking, should I go that way or this way or that way? But I haven't moved yet, right? So A is fixed. And since the gradient is computed at the point A, as I contemplate my options of unit vectors V, the gradient is fixed. It's not changing. The gradient does not depend on which direction I'm contemplating moving, right? So this is constant 2. So in fact, what we really need to optimize, it's as simple as this. We just need to optimize cosine theta. And that's an easy one, right? Total layup. How do you maximize cosine theta? Well, it's maximum when it's 1. Which happens when this angle theta here, that is, notice the angle between the direction I'm seeking and the gradient at the point A, when that angle is 0. And now, geometric appeal, if you need that purple angle to be 0, what green vector makes that purple angle 0? Well, the one that's hard to draw, right? The one that points in the direction of the gradient vector, where again, the angle is kind of gone, right? So, and of course, easy to write down the formula for a unit vector pointing in the direction of a given vector. So nice, crisp little answer to the question, how do you maximize the directional derivative? Go in the direction of the gradient. Simple as that. Whatever direction the gradient points, go that way. Okay? All right. So lovely little calculation. Now, natural next question. The whole point to this was to figure out how to maximize the directional derivative, because I'm interested in that directional derivative. So when I do maximize that directional derivative, what is it? What is that maximum value of the directional derivative? Reasonable next question. All right. Well, again, directional derivative is computed by, wrong colors, of course. The directional derivative is computed by that formula. We just got through computing that this, wrong color again, that this unit vector, the optimal unit vector is that, right? And this is pretty easy to crank out because I have a dot product of a vector with itself. That's magnitude squared. And so altogether, I have magnitude squared divided by magnitude, which gives me, well, magnitude. And so the answer to our question, what is the directional derivative in that direction? The magnitude of the gradient. So in some sense, the gradient was the answer to both of the questions we just asked. What direction? Gradient. What's the directional derivative in that direction? Gradient. All right? One's the direction, one's the magnitude. And I think this is a really nice point of view on the gradient. Now let me just remind you, before just now, what was our point of view on the gradient, right? How were we thinking about the gradient? And frankly, we didn't have a particularly good way to think about it. I guess you'd say we were thinking of it as a notational convenience. It's nice so I don't have to write down, partial derivative, blah, blah, dot, 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 and, have a bunch of terms. It was a shorthand that played the role of a derivative, I guess, was maybe the best we could say. But at best, it was an algebraically interesting thing. We didn't have a geometric point of view on it. Now we do. Now we know the two defining geometric features of the gradient, the direction and the magnitude. Right? This is a purely geometric characterization of the gradient. The direction and the magnitude are answers to natural questions. The direction is the direction of fastest increase. The magnitude is that maximum directional derivative. So you might say the maximum sort of rate of change, or the maximum slope if you're looking at the graph. Whatever. But very naturally, geometrically natural characterization. So total game changer for how we think about the gradient. Right? Very cool. All right, let's see this in action. Here's an example. So we've got a hill, and it's the graph of a certain function. And again, very important. We're looking at a graph here. Calculus is different in every different kind of context that you draw different pictures. Here we're specifically looking at graphs, just to emphasize. And I'm at a certain point on that hill, and I want to know which way is uphill and how steep is the mountain. And by the way, I hope the following little bit of language is well understood. When somebody asks how steep the mountain is, they mean how steep is it in the uphill direction. Right? Like if you're on a steep hill and someone says, how steep is it? You say, well, it's not very steep to me because I'm not walking uphill. Right? That's not what the question is. Right? So how steep the hill is means how steep in the maximum, in the uphill direction. All right. Now there is a subtle point of language we've got to be careful with. And, so be it. I mean, this is just the reality. Let me start with something relatable. When you talk about your location, you're out on a hike, right? And you want to describe your location to the what do they call them? The forestry service people. You broke your leg, they're going to come get you. You ideally give them longitude and latitude, right? And you don't bother telling them, by the way, I'm on the surface of the earth. Right? Most of the time they're going to assume that. They're going to assume you're not flying around at 15,000 feet. They're going to assume that you're not in a mine 700 feet below the surface. They're going to, of course you're at the surface. Where else would you be? I mean, pretty much. So when we talk about location, we talk about map coordinates, longitude, latitude. Altitude not necessary. That's obvious. Right? So little bit of a conflation here. I'm actually at a point in space that has 3 coordinates. That's where I actually am. But I'm only going to describe my location, let's see, I'll do it with this, by map coordinates, namely, again, usually longitude, latitude, but I'm just going to say X and Y here. And it's sort of understood that, well, yeah, of course, yeah, given the X and the Y, you figure out the Z. That's, again, kind of given. So it's a sloppy point, but very often these 2 points are conflated. Now, I made a careful point here of not doing so. Right? Notice I said, we're talking about the point sitting above 1, 3, and I was careful to distinguish them. That's kind of weird, frankly. I mean, most of the time, people don't do that, right? So, and in fact, most of the time, I'm not going to do it either. So heads up, right? I did it carefully this one time, but most of the time, what you're going to see is, hey, at the point 1, 3, which way is uphill? And of course, it's understood that you are on the hill at the point where x and y are 1 and 3. All right. So answer to the question is just a rehash of what we just talked about. Which way is uphill? Well, the direction that the gradient points, which you can see, you compute the gradient, by the way. Easy computation to compute the gradient. You evaluate at the point in question. You get this minus 2, 2, which is like so. By the way, quick side note, don't forget, the gradient is in the domain. Gradient's not a 3-dimensional vector here. Gradient's in the domain. It has one coordinate for each partial derivative. You have one partial derivative per domain coordinate, right? So 2-dimensional vector. So when we say the gradient points uphill, again, we're conflating. What we mean is it points in the direction on the map, which gives uphill in real life. Right? And again, silly distinction, of course. But again, when you get into the math, I mean, it's your job. Part of your job is to make sure to interpret appropriately. And when we say the gradient points uphill, I am not saying that it points this way, because it doesn't. Right? The gradient is a map direction. And again, you can see that's what you might call southwest. How steep is it there? Well, how steep is the magnitude of the gradient. Again, an easy little calculation, 2 root 2. By the way, it's pretty steep. 2.8, it's about like that. That's definitely a, use your hands kind of climb. This is not a stroll, right? That's a steep point on the hill. How we doing? Everybody on board? Okay. All right, so let's talk about level sets. Now, notice the change of gears. We had been talking about graphs. We did a little bit of calculus of graphs, talking about what things look like in a graph setting. Now, total gear change. Now we're talking about a level set. This is not to be thought of as being a graph, even though what I drew, could be reinterpreted as a graph. Vertical line test and all that. But we're going to think of this as a level set. Okay. And we're going to kind of do a little exploring of this scenario and think some stuff through, and a really important fact is going to drop into our laps unexpectedly, I'll say. All right, so keeping in mind, we're talking about a level set. So F is a constant. This surface here, characterized by F being a constant. Level set of F. Okay. Let's suppose that I'm at a certain point and that I'm moving with a certain velocity from that point that is tangent to the surface. Now I'm going to make a modest observation. I think this is very believable. If it's a tangent vector to the surface, then it's literally the velocity vector for a path on the surface. And the path in question here would be something like, let's see here, I'll use, doesn't matter. Something like that. Let's think about this path here. All right, moving like so. And I just kind of arranged that path to go, when it hits the point A, it's going exactly in the direction that that tangent vector points. And I claim you can do this for any tangent vector. I hope that's geometrically plausible. Right? It's tangent to the curve, and the curve's in the surface, then it's tangent to the surface. All right, now again, modest question. Let's think about what is df/ds as I move along this curve. Let me say it a little bit differently. How fast is f changing as I move through this surface where f doesn't change? Well, I said it myself, f doesn't change, right? We're in this curve that's entirely confined to this surface where f doesn't change. So as I move, f doesn't change. The derivative is 0. Yeah? Okay. All right. Well, okay. So here's the thing now. Of course, that works for any tangent vector, and keeping in mind that let's see here, df ds is the directional derivative, and directional derivatives are computed with dot product with the gradient. If I say that df ds is 0, another way to say that is this dot product is 0. Whoa, weird. I have a handy geometric interpretation of that, right? Dot product is 0 means orthogonal, which, again, you know, most of the time, ignoring zeros and silly nonsense like that means perpendicular. Okay, wow. Now that's a weird result. That is pretty unexpected. What we've shown now is that no matter what tangent vector you're looking at, any tangent vector, the gradient is perpendicular. It's perpendicular to all those tangent vectors. That means it's perpendicular to the surface. And so that's the big result. Gradients and, let's see here, gradients and level sets are always, anyway, okay, fine. Are always perpendicular. Everybody see the argument there? It's really handy fact. This is possibly top 3, definitely Mount Rushmore most important facts about the calculus of level sets. Is that gradients are always perpendicular to level sets. And I guess this is a pretty good place to call it. Okay, we'll call it right there. See y'all later. Have a good day. Feel free to discuss the exam amongst yourselves.